the organizers for the opportunity to speak to you. I really like vector bundles, and I really like combinatorial. So, this is a great conference. So my title, Convex Geometry of Projectivized Toric Vector Bundles. The word convex refers to a number of convex bodies that you can associate to a variety. And usually the reason you do that is you want to control the behavior either in a big group or alone, just one of them, of divisors. And so I want to begin by just recalling some simple things about divisors, like why do we study? What's the point of studying divisors on a projective variety? So for the talk, I'm primarily going to be dealing with smooth projective varieties. And the class group will even, I'm just going to go ahead and assume it's free and finitely generated. That will certainly be the case for all of the examples I actually talk about. So remember, or recall, that to a variety like this X, we have this gigantic free group, which is just the direct sum of a copy of Z for every prime subvariety of codimension 1. It's sometimes called div. And then the class group of the variety is this giant free group modulo equivalence, where two divisors are equivalent if they differ by the divisor of a rational function. And then an element in here, say E, is effective if all of its, the multiples, if all of the numbers next to the divisors are non-negative, which I'm just going to write as bigger than 0. So what this means is that when you write E out, it's a full combination of these W's with some numbers next to them. Those numbers are all. Then to an actual divisor, we can associate the linear series, which is this is the set of all effective members of its equivalence class under this equivalence. Yep. So in this case, yes. And if you have a locally factorial variety, that would be the case. However, generally the class group only contains have a Bay divisor, which is not a divisor, or a divisor is a line bundle using. All right, so once you have this notion of this linear series, you get to the point of why you might want to study divisors. So I'm going to let BL denote the base locus. And this is the intersection of all of linear series. You can think of this. So the divisor is going to, as you go through the different elements of the equivalence class of a divisor, you think about them as sweeping over the variety and is telling you stuff about the variety. But then there's points that are common to all of those things. And that can't really be seen by this sweeping process, the base locus. And then the class itself can be identified with a certain projective space, which for technical reasons I'm going to write like this. It ends up being this it's a finite dimensional vector space or a projective space. And then kind of the point is that we get a map. After we remove the base locus, to this projective space. So this is the point of the divisors, is that we get a map to a projective space. And a projective space has, homogeneous polynomial ring as an algebraic object that you can associate. And any subvariety, any closed subvariety of projective space can be described as the zero locus of a homogeneous ideal. And so effectively, we are back into a situation that we're more comfortable with. We can use elements of commutative algebra to understand the geometry of X. This is why we like divisors. And the more information we can get out of this map, the more we like it. And so we think of it as positive. The more positive the divisor, the more information we get out of it. And so that's going to, just looking at this map is going to lead to two kind of natural notions. So, and each of these notions is going to have an algebraic variant and something else that's called a numerical variant. These are properties of divisors. We say that the divisor class is base point free, which I will just abbreviate as BPF, if the base locus is empty. So base point free divisor, for a base point free divisor, you don't need to do this like uncomfortable set minus thing. You actually get a regular map on your variety to projective space. And now you're like cooking with some gas, right? You have some hope now of actually realizing your variety as something that you can handle with a computer algebra system. And then the sort of numerical variant of this is like a semi-ample. Say D is semi-ample if ND is base point free for n sufficiently large. So if you take a big enough multiple of it. Yep. Alex?
Semi-ample.
Oh, okay. What would you call it?
Like any semi-ample variant under.
Okay. I am not an expert at this. However, everything I'm going to deal with today is going to be a Mori dream space, and so semi-ample and NF are the same. So I can go ahead and make that apology. Okay. NF is the same as semi-ample, and that actually gets to kind of why semi-ample or NF is okay. To determine whether or not one of these guys one of these divisors is NF or semi-ample, involves solving some inequalities. Whereas figuring out if its base locus is empty is an algebraic property. You have to do like work with polynomials. All right. So this is sort of the first pass of a positivity property that we're after. Second pass is very ample. The D is very ample if this psi D, if it's base point free, and if map is an embedding. So in this case, you can actually realize your variety is the zero locus of a homogeneous ideal. And that's like maybe what you're really after. And then the stable version of this is ample. Yeah, let's just call it. So the things on the right are easier to test, and the things on the left are what you want. That's the idea. So with this in mind, we introduce the question that I'm interested in. This is the Fujita conjecture. So X is going to be smooth projective that its dimension is going to be D. A is going to be ample. And then Kx is the canonical class. The divisor class is a zero level. There's two of these things. First one is freeness, and the second one is ampleness. And the freeness conjecture says that if you take the canonical class and add a multiple of this ample class, it's base point free if the multiple is bigger than or equal to the dimension. And then ampleness is similar. It asks for the algebraic condition with just one more. So these conjectures are striking and maybe wrong because they assert that you can extract an algebraic thing that you want from the sort of weaker version of that thing, like an ample divisor, right? A is not very ample, it's just ample. And all we're doing is we're adding a multiple that satisfies an easy inequality to the canonical class, and we get, boom, this magical, algebraic property. All right. So this is the thing I'm interested in exploring with projectivized toric vector bundles. So let me say real quick some cases where it would go. For dimension, for let's say it's D less than or equal to 2, both freeness and ampleness are known. So you can prove this for curves of Riemann Roch, and then the D equals 2 case is due to Reader. Freeness is known for D less than or equal to 5. So if you have a full fold, 6. Okay. Cool. 6. So if you have a 5-fold or a 6-fold, it's good to 3. And then it's for cases that are closer to what I want to talk about today. For a smooth, so both fold with smooth projective toric varieties. I'm not going to say that's like an exercise because I really hate it when people say that. But if you have to take a big, long, several years course from that book, Cox Little Shank, and maybe if you read some of Lazarsfeld's book, you could probably cobble together a proof of this. And then freeness is known for complexity 1 variety. By some work of Altman and Hilton. So a complexity 1 variety is like a toric variety, where instead of the torus being maximal dimensional, it has dimension 1 less than the. Oh. Not on those examples, but I'm going to talk about it. No. All right. So now let me tell you a little bit more about projectivized toric. One reason I like this class of spaces is that, like toric varieties, they admit a combinatorial classification However, unlike toric varieties, there are still, like for the fatigue injectors, they're still not known for them. And there are other things about them where their behavior is more complicated than that of a toric variety. But you can still, in some sense, get a hold of them with some combinatorial information. So that's what I'm going to tell you about that. So I'm going to usual toric setup. Sigma is going to be a fan in a lattice for lattice n. The T is going to denote the torus. With lattices and lattice of co-characters. M is going to be the dual lattice. I'm going to assume, so then X sigma will be the associated toric variety, and I'm going to assume that it's going to be smooth and am I wrong? All right. Right. Okay. Now a toric vector bundle, as Kumar mentioned yesterday, is a vector bundle over the toric variety, which is equipped with a lift of the torus action on the base, the linear action of T on the toric on the total space of T. So this is just what it is as a space. Now, a projectivized toric vector bundle, I'm just going to denote by putting the T in front of it. And you can if you prefer geometry, the way you can think about this guy is you go into the fibers of the vector bundle T. You replace each one with its projective space of rank 1 quotients. It's a little weird that you don't replace it with its vector space of lines, but this goes back to when studying these things, and it makes a lot of the notation work better. Another way you can think about it, if you like algebra a little bit more, is you can think about it as the relative product of the chief of polynomial rings that you get by sending each. Some fun things about these guys. So these guys are smooth and projective, and we can compute their class groups pretty easily. They are the class group of the base cross an extra group. Not so bad. And the way you can think about this is this component is pullbacks. From base. So this is if you want to think about them as line bundles. You pull back the line bundles from the toric variety itself, and you get a line bundle in the projectivization. And then this component right here are the stair sheaves that you get when you do a product. And that's all she wrote for divisors / line bundles on projectivized toric vector. Okay, so they're smooth, they're projective, they have a nice class group. Why are they combinatorial? This is going to involve erasing something, so buckle up.
Class group of the vector bundle itself not so nice. I mean, what's the advantage of projection?
Oh, well, that's a relatively alpha guy. We want a projective variety. The vector bundle itself, the total space is not projected. And we're biased towards projective things. So I'm going to tell you about a way to capture these objects with some data, but it's going to look different than the data QRs told you about yesterday. So the data, so to get at these conjectures for projectivized toric vector bundles, I'm going to talk about the Cox ring. And the Cox ring can be computed from the classification data of a toric vector bundle because it's a classification. But I want to present that classification data in a way which makes the formula for the Cox ring a little bit clearer. So that is the reason that instead of talking about a piecewise linear map from the support of the fan to the building, I'm going to talk about L and D are the members of this pair. L is a linear ideal. And we think about the quotient ring as being the polynomial ring that you get when you sum the sim powers of the general quarter. So like you have a torus vector bundle. Think about the torus as an open subvariety of the base. The torus has a point on it, the identity. Look at the fiber above the identity, call that E. And we want to imagine that sim E is this quotient ring. So you might ask, why not just write this as a polynomial ring? Why are we writing it as a polynomial ring quotient to linear ideal? And that's because the data of the toric vector bundle needs this more enhanced, inefficient presentation to seal. It's going to be part of the thing that is going to be matroid defined L on the elements Y1 through Y. That's why we're being a little inefficient. And then D is going to be an n by m. I'll say what n is in a second. Integral matrix. And then D is going to have to satisfy some additional properties, which I'll get to in a second. So here n is the number of rays in the fan. So when you have a fan, you need to put a number in parentheses next to it. It means look at the collection of faces of that dimension. So the one-dimensional faces are the rays. This is the number of rays of the fan. So this is a matrix where the rows are in bijection rays, and the columns are in bijection with these variables 1 through n. And now we have to assume two additional properties about this pair in order to introduce it. So if I write D as a collection of rows, I'll write it like this: W1 through Wn. And we need the following properties. So each of these rows must be an integral point on the tropicalized linear space defined by the linear ideal. M is not the rank. The rank of the vector bundle from this is M minus the dimension of L, if you think about it. All right, so now we're in the world of tropical varieties and Bergman plans of matroids, if you want. The second property also has to deal with these sorts of fans that you can assign ideals. So the second property is that for every face, there is a face, a corresponding face. Of the Gromov. And then all of the rows indexed by rays that correspond to rays in that face you started with have to live in that face of the Gromov. So I like to think about this as like a combinatorial continuity. If you start out with rays that are close together on the fan in the sense that they use a common face of the fan, they have to land in a common face of the Grosvenor. Excuse me? Well, they do, as points, they all do live in the Bergman fan. But I'm saying, if you look at them as a collection, there's a common face of the Grosvenor fan that contains them, but not necessarily a common face of the Bergman fan. They have to live in what's called an apartment by our notation of the Bergman fan, but they don't live in a common face of the Bergman fan. Does that make sense? So I can show an example. Maybe an example will clear it up. Okay. So I will at least start and maybe probably finish with my favorite example.
The piecewise linear curve.
That's right. I will also explain the connection which you were taught yesterday. But an example of this table. We look at the tangent bundle of P2. P2 is toric variety. The tangent bundle is a functorially created vector bundle from that toric variety, so it inherits the toric action, so it's a toric vector bundle. The L in this case is an ideal on 3 variables generated by the linear form that you get by just summing those 2 variables together. The world's best ideal. And then the matrix is a 3x3 identity matrix. And after making some hemmings and hawings, that's the form that all tangent bundles of toric varieties take. Their D is an identity matrix, and their L is the ideal of linear relations that hold among the ray generators. So the fan of P2, right? I said tropical geometry, and here we go. He's drawing the picture. That's the fan, both the rays of the fan of P2, and they satisfy, the ray generators satisfy this plus this is 0. Right, and so that's the one, that's the relation. Of course, for a more general toric vector bundle, there's not this sort of feedback between the space and the data because it's not functorially. All right, so thinking about the tropical variety of this guy, it looks just like this, except there's an extra direction. So let's ignore the extra direction for now. The rows of this diagram then are these 3 points. Right? That's where they get mapped. And if you look, they all live in the Bergman fan, right? But if you take any face of P2, that's taking 2 of them together, and they're not going to live in a common face of the Bergman fan, but they will live in a common face of the bigger Grosvenor fan, which contains it. So the connection between this data and the data Kumars told you yesterday is as follows. You can imagine this assignment here, this matrix, as a map from sigma 1 to the tropical variety, right? So if you think about that as then a map which assigns each ray generator something in the tropical variety, you could take the spans out and get a map from the spans of the rays to the tropical variety. Then it turns out there's a unique way to satisfying some nice conditions to extend that to an actual piecewise linear map on the fan to the tropical variety. And then a point on a tropical variety can be put in bijection with a weighted filtration of or a weighted flag of flats in the underlying matroid, or a filtration by vector spaces. And that ends up by some stuff Kumar said yesterday, being the same as a point on the spherical building for GLR, where R is the rank. So there's a unique way to map this tropical variety into the building by thinking about it as weighted flags of subspaces. And so that gives Kumar's map. So if you like I really like, obviously, the stuff Kumar talked about yesterday, since my face was involved. And that's a nice way of thinking about some geometry attached to the combinatorial data of a toric vector bundle. But this L&D is much more direct for computations geometry. If you want to like go into a computer and ask, dear computer, is this toric vector bundle nice? This is the data. This is an example of the data that might. The linear ideal, explicit linear ideal, and an n by m integral. All right. So now let me get to the point of why I want to like switch things up on you with classification. So this data, I think, is this L&D data is a little bit better at getting properties of divisors on the projectivized toric vector. It's not 1-to-1. That was one of the comments I forgot to say. So different L&D can give the same. So this is cool. Different L&D can give the same toric vector. Some L's are better than others at seeing certain properties. So if you've heard of this work of DeRocco, Gabush, and Smith on the parliament of polytopes, they find that there is a representable matroid that you use to define this parliament. A representable matroid. That representable matroid, if you look at the linear relations generated by the circuits of that matroid, that could be a potential L. And that would be a great L for detecting global generation and ampleness. But smaller L will also work. They just won't sort of contain enough information off the bat to see those properties. However, there is an algorithm that Kumars and I defined that you can ask Courtney about, which will compute generators of the Cox ring of a projectivized toric vector bundle. And that can actually complete the L to an L like the properties like the DeRocco. So the map is many to one, but for any toric vector bundle, you can find AL, which does it. All right. Cool. Oh yeah. And let me take advantage of this pair to point out some special toric vector bundles that are worth a further look. So for the remainder of the talk, I'm going to assume L and D give your favorite toric vector bundle E. So we say E is sparse if each row of the diagram has at most one non-zero entry. I forgot to say something else. I apologize for this. If you take a diagram D and you add a common integral entry to every entry in a row, that is the same as tensoring the line bundle, the vector bundle by a line bundle. That operation is not seen by projectivization. And so without loss of generality, if we're talking about the projectivized toric vector bundle, we can assume that the minimal entry in each row is 0. So if we have an integral matrix with the properties I mentioned earlier, but the minimal entry in my 5th row is -7, I can just add 7 to every entry in that row. And all I've done is tensored by a toric line bundle, which does not change the projectivity. So we can assume. And this is important because sparse bundles, it turns out, behave very well, but then any tensor of them with the line bundle also behaves. And so then this condition wouldn't be satisfied, so it's sort of annoying. Okay, so we say it's sparse if each row has at most one non-zero entry. And so like, here's an example of a sparse bundle, right? So this class includes tangent bundles of smooth toric varieties, any rank 2 bundle, and it's the same as a class of bundles studied by Gonzalez and Payne. So it turns out, I'll say this again in a second, but the projectivization of any sparse bundle is a Borg group. It's a very nice class of bundles that contain sort of all of the known cases of Borg groups. So we're going to say, and I like to think about sparse bundles as the bundles you get when you make the diagram as simple, the matrix D as simple as possible. The next class I like to think about as you make the linear ideal L as simple as possible. We say E is uniform if the linear ideal is very general. And what I mean by that is that the matroid that you get from the linear ideal on the generators y1 through ym is a uniform matroid rank R on M elements. Right. So if you asked for a matroid on M elements that was rank R, this is like the easiest one to do. All right. And then last but not least, I'm going to say that E is monomial. Certain ideals, I'll say what they are in a second, that you get from the linear ideal are monomial ideals. So this is the initial ideal associated. Remember, the rays of any face sigma get mapped to a face of the Grosvenor fan. And if you look in the interior of that face of the Grosvenor fan, you can take a weight from the interior and define an initial ideal. So you want that initial ideal to always be a monomial ideal. Yeah, out the. Right. So I said, yeah, this is getting a little. E is monomial if the initial ideal in sigma L that you get from any face of the fan, a maximal dimensional face, is monomial. So this class also contains tangent bundles. These are just 3 times the thing. Sigma. So this, yep. So these are just examples of like staring at this data of some conditions you could put on the data of the toric vector bundle to maybe make it behave more nicely. Let's see if they do this. All right. So now I want to mention the Cox ring of a projectivized function. So the Cox ring for X, for a general variety X, I should put that over here, is the sum of the section spaces of the divisors. So this is a little bit of a lie because for every divisor class you have to pick a representative, but you can do this in a uniform way. And so you get a ring.
Like you, he is different from that.
Yes, this is a divisor. Okay. No, I'm not gonna make everybody happy. And and I don't need to try. Right, so you can think about the Cox ring as it's like a coordinate ring, but it sees all of the information of any coordinate system you can put on X. And we say this dot is X is more in dream space. Now, this ring is finitely generated. So when you have a finitely generated Cox ring, you could write that information down in a finite length file and then send that file to your friend, and they would have sufficient information to extract any projective coordinate system on your board. Okay, so the point of this different type of classification is it gives us a way to write down the Cox ring. So to do that, I'm going to define certain subspaces of this quotient ring that I mentioned earlier. So we have this linear ideal. I'm going to call the quotient map phi. And then for every row of our matrix, we can write down the following subspace. It's all the elements in phi where there exists a polynomial mapped to that element, where when we write that polynomial out, space here, and we've got our ith row with the exponents that appear in that polynomial, we always get numbers that are bigger than or equal to this lower index part. This is a vector subspace of this polynomial ring. And it's a piece of an algebraic filtration on the polynomial ring. I'm going to write B here to mean that the degree of the polynomial we found is B. So this is information that we can get entirely from L, there's L, and D, there's the ith row of D. And so this allows us to define a ring I'm going to call RLD. This is a big sum over Z to the n cross Z, where the R's belong to the Z to the n and the D belongs to Z of these cases. And we intersect them. So once again, this is a ring you can write down purely from the data of L and D. This ends up being the Cox ring of the projectivized vortex. This is nice because it's, in some sense, even though it's sort of nuts, it's explicit. These are polynomials that satisfy specific inequalities on their exponents, which is a thing probably better than we. And indeed, it's a subring of sim E with n extra placeholder variables. Yeah, right. You can do it that way. You can do it as a subring of the Laurent polynomial ring of n variables over sim E, obtained by intersecting the level spaces for n valuations. But it's known that Cox rings of projectivized toric vector bundles are not necessarily finitely generated, and so even though this is in some sense not a terrible thing to write down, these guys can be infinitely generated. I also want to mention that something I'm not going to get into, but you can view these spaces in terms of the parliaments of polytopes, if you're into that story, for the higher sim powers of E. And so in some sense, any ring that looks like this has a combinatorial parliament picture attached to it, if you stare at it in the right way. So that includes blow-ups of points on projective space. That includes the Cox ring of M0n bar. There are lots of rings that have can be viewed as an RLD for specific elements. It does by definition, but different L and D can give the same ring for sure. Yeah. If L and D give the same toric vector bundle, they're going to give the same ring. All right. I'll just say in words, there is some partial progress that one can make on understanding these rings. So I mentioned earlier, there's an algorithm that we've written down, which given the L and the D, will produce a generating set of RLD as an algebra, if there is one. So you might have not written, you might have chosen your L and D poorly, in which case the procedure will run forever. You may have also chosen an L and D poorly in the sense that it has more generators than there are protons in the universe, and that could run effectively forever. But for certain L and D, you might luck out, and this algorithm might give you an answer after 2. So there is a procedural way to determine whether, positively, if the projectivized toric vector bundle is a more true space, but can't classify. We also have a condition on a certain ideal and a tropical variety of that ideal to check if your favorite generating set is a generating set. That isn't just the algorithm terminates on it. So those are just some comments. I want to make a definition real quick, and then I'll get to the actual strategic conjectures. So I'm going to say that a projectivized toric vector bundle degree 1. This is a terrible working name, and I understand it's terrible. You don't need to tell me. Okay, Alex. If its Cox ring is generated by the spaces of the form, this D I wrote over there is just a 1. Oh, yes, 1. We call those degree 1 or sim degree 1 in connection with this, the sim powers of the toric vector bundle. So you can think about
you can say generated in
it's generated in degree, but that's just more words. And now there's even more words being said to explain how that's more words. So I want to say real quick that degree 1 bundles are plentiful. And in some sense, all of the known cases where RLD is generated, not all of them, but the big families of them are degree 1. So for example, rank 2 vector bundles, toric vector bundles, tangent bundles of smooth toric varieties, and they're generated. And then there are other examples as well. For example, there are uniform bundles where you can articulate large families of the D, where it will only be. In fact, we have a theorem that gives a combinatorial classification given an L, which these will give you something in degree 1, where the ideal of relations has is a complete unit. So the point being, these are plentiful, and they're also they're nice for this reason. So this is say this is a lemma of Courtney, George, and myself. For any maximal flat in the matroid of one of these initial ideas that I mentioned earlier, there is a point, distinguished point on the projectivized toric of the bundle. Sigma lives in the fan sigma, but remember we have a way of mapping the rays into the tropical variety, or and more generally the Grosvenor fan. So every sigma needs to have a face of the Grosvenor fan that it lands on, and so it has a well-defined initial ideal for that. Because sometimes you land in a face that's not maximum. And that's why monomial bundles are super cool, because you do land them on. Okay, so there's a point. I'm going to let S sigma F be the monoid generated by the divisor classes of the generators of the Cox ring, which do not vanish on this point. So for this, you don't need to assume anything. But then if PE is degree 1, then the monoid of base 0.3 divisor classes on PE is the intersection of these monoids, where you run over all bases and all maximal flat stack. So if this is one reason why one of these degree 1 bundles are interesting, because the monoids of base 0.3 divisors can be explicitly described in terms of some matroid data. Okay. And that's what allows us to get at the Vegeta conjectures under lots of assumptions using this system. Say again? No. So for you really need the degree 1 part. One consequence of being a Murray green space is there always are a finite number of points somewhere on your space where the base 0.3 monoid is an intersection of monoids. But then you have to find them. So the point of this result is like that there's these distinguished points, and those are the ones you can pick. Okay, so here's some. This one is if. So I'm always going to assume that PE is degree 1. If PE is monomial, then any net class is base 0.3, and space is Vegeta free. Satisfies the Vegeta free. Second consequence. If PE is over a product of projective spaces. So this can be these bundles in point 1 over any smooth projective space. You're over a product of projective spaces. And you have a uniform bundle or the source bundle. Then any F class is base 0.3. Any ample class is very ample. And the space is both Vegeta free and Vegeta ample. So I want to say real quick that this class actually contains all tangent bundles of two projective toric varieties. So one consequence is any projectivization of a smooth, the tangent bundle of a smooth toric variety is And the third seems like it would be a subclass of the second, but it surprisingly isn't. And I'll say some more comments about it in a second. If E is a rank n irreducible toric vector bundle on Pn, then this stuff holds. Then nap implies base 23, ample implies very ample, and space is both equal to 3 and ample. So I really like this third class of bundles. So if you remember at the end of Kumar's talk yesterday, he gave some splitting criteria. You have a toric vector bundle on projective space whose rank is less, strictly less than the dimension of that vector space, then for matroidal reasons, basically, has to split into a direct sum of line bundles. In which case, its projectivization is a smooth projective orthogonal. And so all of this stuff will work. So the next natural case to look at are rank n bundles, which don't split into smaller bundles because then they would split into line bundles. Yes. So the tangent bundle of projective space and its cotangent bundle are both sort of special examples. But those are remarkably nice spaces, which I don't have any more time to tell you about. Probably an application. Very much like these spaces. Thank you for listening.